Thank you all very much for coming. I am excited about this kind of a crowd. This is something that's really grabbed my interest. So I like talking about it. I find it's fun. And usually every time I talk about it, I learn something about it. Because someone asks a question or they tell me something or they tell me what I hadn't thought of. So this is great. So my name is John Lingle. I was actually trained as an experimental social psychologist. And that's sort of relevant because 50 years ago, I was bringing freshmen into the laboratory and running them through psychology experiments, trying to prove causation, trying to prove my hypothesis about what was causing what. So I've been kind of interested in causation for a lot of years. And that was one of the things, come on baby, that was one of the things that got me interested in Judea Pearl's book of Why, and I originally bought the book and I started reading it and I got excited and I sent it to people. And in a lot of ways this is sort of a book report of this book, so why didn't I just tell you guys to go buy the book? Why would I give a book report other than it's fun to be back in the 7th grade again? It turns out about a third of the people that got excited when I gave them the book quit reading it, and they didn't get through it. And I think there's a couple of reasons for that. One is the concepts are a little bit complicated. Also, it's counterintuitive and against everything we were taught in graduate school. So I think some people were put off by that. This is mumbo jumbo. Everybody knows you can't prove causation with correlation, so why do I need to read this? And then the third thing, I think parts of it aren't very well written. And so that sort of put people off because it gets hard to understand, and part of it is the writing style. So, but I really got interested in it because it challenged how I was trained as a statistician, and I've reached that age where every day I learn something I thought I understood I didn't understand, so I look for such things out there. I think, as does Judea Pearl, he argues, that this will significantly change how we do science as we go forward, and it's going to form the cornerstone of strong or autonomous AI. Machines are going to act like people on their own. They're going to have to figure out some way to form causal hypotheses, test them, work them through. So for all these reasons, I got interested in it, and I'm trying to get other people interested in the book. So I thought I'd just start by, this is what I hope you'll take away from the talk. Let's see how good I am at convincing of this. That causal models are critically important to how we think and how we make decisions as people. You can get strong evidence from correlational patterns to support causal hypothesis. This is where all the statisticians get up and leave the room. This new way to investigate causality will likely change science and also be part of our AI autonomous robots. I'm hoping you'll walk away with a good feel for how this new approach works. I'm not going to get down into the weeds. I'm not going to get into the mathematics other than to give you a very high-level sense of what's happening, but I'll point you to a book if you want to get down into the weeds into the mathematics. I'm going to compare some of the pros and cons of this new approach compared to the old approach. I don't think either one of them is going to go away for a long time, so let's see what some of the pros and cons are. And as I said, I'll point you to some resources where you can learn more. So who the heck is Judea Pearl? Now, some of you who've been in the machine learning area may have heard of him. He's kind of famous, and particularly on the Bayesian probabilistic approach to AI. And he's also credited with designing or developing a lot of this causal modeling stuff. Very well educated, but eclectic. He's got a couple of different degrees there. So interesting fellow just in terms of his worldview. And a fair number of awards down here at the bottom, including the ACM Turing Award. For those of you not in computer science, that's sort of the Nobel Prize of computer science. So he's been well decorated. Obviously, a lot of people make the guy knows what he's talking about. The way I'll go through the topics is I'm going to spend a little bit of time with a quick review of traditionally how we went about testing causation, because I think that sort of gives you an understanding of comparing the new methods to what the old methods were. I'm going to try to give you that conceptual framework. This is what they're doing. If you can't understand it in the first third of Mr. Pearl's book, keep at it. This is what they're going to come up with. It isn't making me nuts. And then I'll give you some resources for learning a little more. And the final thing, sort of my main motivation for being here, is to try to see if I can find other people who are interested and might want to form a study group. I am not a mathematician by training. This stuff gets pretty complex. And so I figure I need all the support I can get if I'm going to try to figure out how to use some of it. So that's my secret agenda. I might ask you, if you can, hold the questions. I mean, if there's something you don't understand, you didn't understand what I just said, by all means stop me and I'll repeat it. But about the last third has all the good stuff in it. So I just don't want to go down the wrong rabbit hole and not get to that last third. And I'll stay here as long as you want to answer questions. Of course, me answering questions may only take about 15 minutes and I'll be out of knowledge, but I will stick around for you. All right, so our interest in why starts early. How many here are parents? You know, how many times you sat there and watched your kids and they dropped the darn pot lid onto the floor, and now they need to do that 683 times to bring their little necks. So very early, kids started exploring relationships, correlations, you know, what things are related. But very soon, they discover the word why. So now they're no longer satisfied with what goes with what. They want to know why, Daddy. Why did that happen? Why does this happen? Why does this happen? Until you go nuts from that. Why is really a causal question. And it's interesting, it's not about relationships. Why is about the process that created the relationship. So if you think about a moment about, say, the Zika virus, there's a nice correlation between climate, tropical climate, and incident of Zika. So if you're a pregnant person, one option is just don't go to tropical climate. But if you have a causal explanation of what's the process that created that correlation, you suddenly have other options open to you. You can cover up well. You can smother yourself with peat. Whatever you do, that's because you've worked through what's the cause of that, what's creating that correlation that's there. So it's pretty important to us as humans and how we work, how we get through our complex world, that we can generate these causal hypotheses and begin to act on them. But it's tough for us. It's really hard. I don't know if everybody can see this, but this doctor's saying it looks like all those tests you took caused you to get cancer. Or if you think, you know, how many gamblers have you seen start blowing on their dice? So people get very confused by this causation question. It's a tough question, and in fact, it's so tough, we've actually created a formal process to try to study it, which is the scientific method. These are typically the steps that are outlined in your first book of science, your first textbook, Science 101. You make an observation, you form a hypothesis, you make a prediction, you go out and generate an experiment, you analyze your data that comes back from an experiment, you either accept or reject that hypothesis that you formed, you revise it often, and then you go back and do it all over again. So this is a formal process, and it's been around for a long time. And often a hypothesis is in fact a causal model, or it can be. It doesn't have to be. You can posit, oh, there's a relationship between, which isn't a causal model. But if you say the crowing rooster makes the sun come up, suddenly you got a causal hypothesis that you you got to check out. A little bit more serious, smoking, leads to buildup of tar in the lungs, that leads to increase in the probability that you'll get cancer. So these are causal hypotheses that get studied using the scientific method. And it turns out the gold standard is the controlled random trial or the controlled experiment for investigating causation. And what that involves is you have a hypothesis. Let's just, for the example, say drug A, leads to increases in the good cholesterol, your HDL. So what you do is you go out and randomly select someone from the population you're interested in that you hope is representative of that population. You then randomly divide them into two groups. And you give one group the drug, and the other group you don't give the drug. And then you take the average of those two groups to see whether, on average, their HDL is the same. Now, the critical piece of this is the random assignment, because that's designed to control all the variables you're not interested in. In theory, if I randomly divide two groups up, they will be identical in all areas. Although you do have some sampling error. We'll get to that in a minute. But that's why you're doing that. And then you're hoping the only way these two groups are different, because you randomly establish them to be similar, is through this administration of the drug. So you compare the two groups. You figure out, you decide either the average of the two groups is the same, in which case you reject the hypothesis, or you conclude these two groups are different on HDL, and it was my treatment that did. So that's the process. My mini research indicates it was first sort of played with in the 1700s. Some of the agrarian scientists who were trying to figure out how to really determine what was causing what. And so it's been around a long time, and it's what I learned in graduate school and what I did over and over and over again to Ohio State freshman. So this is what, people say, oh, correlation. That doesn't prove causality. And they say that almost as if this does prove causality. But we're going to have to slow down here for a little bit. There's a couple of things. Number one, your conclusion isn't proof, it's a probability. So you say the groups are different with a 95% probable chance. That means they could be similar 5 chances out of 100. So you don't have proof, you have evidence. You have some pretty strong evidence that the drug might have impact, maybe. But even that's not so simple. Even that probability is suspect, because all kinds of things can go wrong. The first thing that often goes wrong is sampling error, or selecting the groups, the two random groups. Sampling error, just look what's happening to the polling people these days. They can't predict their way out of a paper bag. And part of it is they can no longer draw a representative sample because we've changed our communication methods. So if you can't get that representative sample, your probability is really messed up. The second thing, when you randomly put people in two groups, even that can introduce some biases. One, for example, with drugs, if I have my treatment group, and I tell them, now you all have to go home and take this drug, and I have another group and say, well, you don't have to do anything, and half my treatment group decides not to take the drug, I'm not taking this experimental drug, I'm taking my money and I'm going home. Suddenly, you no longer have random groups, so they're not going to be, this group has lost all the money, or, still doesn't have its money-hungry ones trying to build up. So even that probability is suspect. And also your treatment may introduce some kind of bias. So this is why doctors have double-blind experiments, because sometimes just giving someone a placebo and saying, try this drug leads them to feel better. There's all kinds of other ways in which you often, when you do a treatment, get you in trouble. So the conclusion I just want to emphasize here is therefore you can't gather evidence that a drug caused the change of HDL. You can gather evidence, but you can't prove it. And the same is true of the new method. All we're going to develop is probabilistic evidence that we've got a causal relationship here. All right, so let's talk a little bit about the new approach. Now we're getting into it. The fundamental beliefs, there's a few sort of fundamental beliefs here that just underlie everything we're going to talk about. The first is you can't prove causation, but you can gain very strong probabilistic evidence of both the likelihood and the strength of a causal relationship. Now, what I mean by those two, the likelihood is sort of a probability estimate, just like a traditional view, because you're doing sampling and things, you're going to have some error in there, so you will have, 95% chance it's within these bounds. But the strength of the causal relationship is interesting because you actually compute, if I do this, how much an impact is that going to have on this variable, because a lot of things have multiple causes. And those different of those causes can have a bigger impact on your dependent variable or the thing you're looking at. Sometimes, 70% of it, what's happening to that variable can be cause A, but then you may have causes B, C, D, and E that are causally contributing to what it is. So the evidence of causation can be gleaned from correlational patterns or conditional probabilities. The other way, one way to think about correlations is just conditional probability. You cut your data set, find that relationships that way. So this evidence can be collected from large pre-existing data sets. You don't have to do an intervention. The influences on causal relationships of confounding or spurious correlated variables can be calculated and removed using Bayesian conditional probabilities and by simulated intervention. Now, when I say a confounding or a spurious correlation, what I'm referring to is things can be correlated without having one causing the other. There are going to be some kind of other intervening variable that's causing that correlation, but it's not a causal link. And I'm going to talk more about that in just a second. But this approach actually lets you explore and examine those kinds of confoundings in a way that's not traditionally done with the traditional approach. So the new approach really has 4 cornerstones that sort of make it possible. At least this is my conclusion from reading Judea Pearl. We're a little bit over in John Lingle's world at this point. But this is what they seem to rest on to me. One of it is a more precise definition of what causation means. If we're going to represent this mathematically, it can't be this sort of airy-fairy definition of what causation means. So the first thing they've done is really define more clearly what do we mean by causation. And it's sort of been implied, if you look at how people do their testing in the traditional method, but it's never been formally defined and mathematically defined as it has now over the last decade or so. A new mathematical operator, as if we don't have enough, right? Go right there with plus, minus, divide, mod. Now we have the do operator, and it has its own wondrous ways of working on data. So we'll talk a little bit about that. A more precise definition of confounding. I sort of said, well, something out there is causing this correlation. That's not something we can represent mathematically. So we're going to actually define types of confounding variables with such precision that they can be represented mathematically, or Pearl is. wheeze probably. And finally, Pearl calls it due calculus. I think it's closer to due algebra, but that may be because I haven't gotten advanced enough to start the calculus part. But basically what the due algebra is it links that due operator to Bayesian probabilities. You know, I need to use my operator to solve equations, figure out conditional probabilities, link doing something to changes in the probability that something's going to happen over here. And so we need a algebra, mathematics around that. So these are the four things that sort of underlie this new approach. So let's talk a little bit about the more precise definition of causation. Pearl argues that there's really three things that you have to have strong evidence for correlation. One is an association. Okay, so we do expect to see that correlation. If A is causing B, or rooster is causing the sun to rise, we expect to see a correlation there. But a second thing you really need for strong evidence is an intervention. When I do X, it influences Y. So if I went and goosed the rooster at 3 a.m. in the morning, assuming he crowed, I don't know what roosters do under such conditions, but assuming he crowed, if the sun suddenly came up at 3 a.m., I would have much stronger evidence that, in fact, there was some causation involved here. But there's yet a third one, and this one occasionally gets tested for in the traditional way, but it's been overlooked a lot, and that's what's referred to as counterfactual evidence. That means if I don't do it or stop doing it, does the sun not rise? So if I put my hand over my rooster's mouth, does the sun still rise? And if not, one more piece of evidence that I've got causation here I'm dealing with. So all three of these pieces of definition actually end up getting used in some of these calculations that happen in algebra, and they make it possible to do some of the things that they've done. And they developed over the last really 10 years, maybe 20 years. It's interesting, in my years in graduate school back in the 70s, I read about path analysis and list roll, and actually started to look into it, and all the statistics professors poo-pooed it and said, quit bothering me, you can't prove causation with correlations. But here we are a few years later, and people are writing books about how you can prove causation with correlations. Okay, so what's this new operator? You know, that was Cornerstone too. I can tell people are excited now. Huh? Okay, so let me start for a second and just say there's a fundamental way, so I'm going to show an equation here, so I don't want to lose anybody. A fundamental way you can think about causation, and this isn't all three pieces, but this is a fundamental way of saying it. If I have some level in the population in the universe, and I change that by doing something, that suggests causation. So for example, if I somehow, or if I know what the cancer rate is among non-smokers in the United States. I know how many cases of lung cancer. You know, what's the probability of getting lung cancer if you don't smoke in the United States of America? And that's my universe. And then I grab 100,000 people and make them smoke, introduce them to smoking, getting them excited they smoke. And then I go look at the probability among that group of 100, and my probability that they had lung cancer is higher my university as a whole. I've got some evidence of causation. And you can represent that mathematically with our famous due operator here. So it's probability of getting cancer, and this symbol is just a mathematical symbol for given that I do smoking, that probability is going to be greater than the probability of cancer in the whole universe. All right, so that's a pretty good piece if I can do that. You're probably going to see the formula like this. I wanted to spell it out because don't want people to get lost in the letters. But this is the way it's written in Pearl's book. So this is the first of the equations. I guess I showed you two equations. This is the first one. And I'll show you one more. But a pretty important one because it shows the first use of the do operator. So cornerstone number 3, confounding. Let's talk spurious correlations, because that's the foundation of the argument you can't prove causation with correlation. And it turns out there's a couple different types that they've now done a much better job of describing. One of them is what's called the fork. Now in this situation, you actually find a correlation between shoe size and reading ability. So if you want to conclude having big feet makes you read better, go talk to my wife, the librarian. She's going to argue that's not the case. What's happening is you've got this type of confounding that's created by the fork, or called the fork, which is a third variable that's related to both of them, and therefore gives the appearance that shoe size and reading is correlated when it really isn't. All right, so that's one type. I guess the other one we used to always say in Ohio, when people eat ice cream, they get violent because there's a nice correlation between eating ice cream and violence. But it turns out what happens in the summertime, everybody eats more ice cream and gets a little more violent. So that's another example of the second one. Another one's the mediator. The fire alarm's kind of interesting here. Oh, you know, the alarm went off because of the fire. Well, yeah, yes and no. What happened is the fire generated smoke, and it was the smoke that was the direct correlation. It is the mediator between fire and alarm, so if you have a correlation here, yeah, it's sort of in the causal chain, but it's not the direct cause of what's making the alarm go off. Just try having a smokeless fire, see how loud the alarm rings. So the mediator is the second type. The third type is called, and this is the last one, so you only have to learn 3 things in this talk. Yeah?
Good, I'm into it.
Okay. This one's called the collider. And this one's kind of interesting because you're never quite sure what's going to happen. It sort of depends on the relationship of various factors and what kind of database you've got. But this is a case where you have 2 independent factors, talent and beauty, an example I used here, which Pearl used also, have an impact on the likelihood someone will be a movie star. But these 2 really sort of act independently, and that can cause several things to happen. And in many cases, it just wipes out the correlation between talent and star and beauty and star, because those 2 aren't related, it just doesn't show up. Sometimes it can actually create a negative correlation in one of them. So some of you are looking at your data, and you have a negative correlation between talent and movie star, and you don't quite understand that, other than people who prefer blondes or something. So this is the third type of spurious or confounding relationship that can mess up your correlation and make it hard to figure out whether you have a causal relationship or not. These things can get pretty complex. This is actually a real causal model that was developed and tested by these people over here, Andrew Forms and Elizabeth Williamson, and it was a model, a causal model between smoking and likelihood that you'll get asthma. And I'm not going to go into all the factors because I don't even know what all those little factors are. The important thing here is if you study this for a little bit, you're going to find our 3 favorite candidates. So here you see a fork, this G, whatever the heck that is. It's going to create some kind of spurious correlation between smoking and asthma. Okay? Over here you see B's a mediator between C and smoking. So that was another one we looked at. And finally, this is a little collider. And these two factors are having an impact on V. So here was sort of the big revolution. Boom. They mathematically proven that these are the only three types of confoundings you can have, which suddenly does make this a tough task, but not as tough as if you had an unlimited set of confoundings that aren't classified or defined or identified in any way. So this was an important part, and a lot of the work over the last decade has been directed towards understanding these confounding and figuring out ways mathematically to filter them out or block them, or in some cases actually run simulations that allow you to compute that relationship between S and A without getting them screwed up with all these confoundings coming into it. So the final thing is we're going to have to do a little math here. Is we've got to link that do operator to Bayesian probability. I already did that with one very simple formula for you. So this is a little bit more complex, but not too complex. And I'm going to take a concrete example to talk through that's actually a real life example. So in this case, so consider the following causal hypothesis: smoking causes cancer. And in fact, that was proposed back in the 70s, and data was provided that showed that. But our friends, the smoking industry, said, nah, I'm not so sure. You know, there could be a gene that people have that both makes them more likely to smoke and makes them more likely to get cancer. What kind of confounding is this? Anybody remember? This isn't a fork. That's okay. So they argued very, and here's the crazy thing. There's something called Simpson's paradox. Does anybody know what Simpson's paradox is? Here's what Simpson's paradox is. You can take a data set and try to correlate something like smoking with cancer, and you get a positive correlation. But if you take that data set and break it into subgroups, and in those, like maybe you break it into male and female, two subgroups, and then you run the data, you actually find the reverse. That smoking actually makes both for the males and for the female groups healthier for you, less likely to get cancer. And this has driven statisticians nuts for decades. And one of the interesting things about causal model is he actually shows you how to develop a causal model that explains it as to what's going on in the paradox. But the drug or the smoking industry, smart fellows that they are, or they actually got some data that as a result of the paradox actually made it look like smoking was more healthy for these subgroups, even though there was this correlation, this negative correlation between that. So it seems almost impossible. How the heck, if this is what they're arguing, you know, I can figure out this relationship, but I have no measure of this gene. No one even knows that it exists. So how can I figure out, and this is the core question, how can I figure out smoking and cancer when it may have this third element that I can't measure and can't even see? Now, traditional method, how did it handle this? It did random assignments to groups. So my two groups, on average, will have the same number of smoking genes. Okay, so I can then get one group to smoke if I'm unethical, which they did actually. And compare the two groups on average, and that's how I take care of it in the traditional method. But that's not an ethical experiment, and that's problematical. Is there any way we can do it in the new approach to causation? Well, in fact, there may be. And consider this for a moment. As I look at my data set and contemplate these scads over in the back over interested in making this argument, I noticed that I have some more data in my data set. I've got tar levels. I have a data set that has whether or not people smoke, what level of tar buildup do they have in their lungs, and whether or not they got cancer. And there's been some research suggesting that maybe higher levels of tar cause a higher probability of cancer, and in fact, you do find that correlation out there. So I could look at this. This could be in my data set. How does that help? What does that do for me? Well, you have to think back to algebra. Remember when we had all those unknowns and we couldn't figure out how to solve? And we needed to get all the x's over to the left and all the y's to the right, and there was this, we had to somehow get rid of things. And the way we did it in algebra is we got multiple equations. We solved one of the equations for the value we needed, and then we substituted that into the other equation. In a lot of ways, that's pretty analogous to what's going on here. That's a piece of the magic and a big piece. So these three inequalities now, I can figure out those probabilities, and I can use those to plug them into my equations. So those three equalities allow me to isolate the do query over to the left of the equation, if I can get it all out of the right of the equations. And I can actually get rid of that gene factor and still be able to solve for the other two, for the relationship. So just so you see the formula, this is actually the formula. Like I said, I can give reference when we get done here that you can go and delve into exactly how this was derived. You see here, the queries over here. You look all through here, unless I made a typo, you don't see that G anywhere in there. So life's good. We can solve this equation. And we can come up with the probability that someone will get, probability A if I do S. And S is smoking. I think I took this from the asthma example, so that may be why that's A. Okay, a couple of conclusions. More precise definition. Okay, a more precise definition of these things has allowed us to mathematically calculate the strength of a causal relationship between two variables, even when the relationship is confounded by other spurious correlations. Don't worry if you hate algebra. We don't all do the calculus every time we do a gradient descent with machine learning. And there are now packages that have come out in the last year in the public domain. I'll give you a link to one of those. So just so we're clear, in the new science that's evolving, or the new way for investigating causation, you hypothesize a causal model, including confoundings that you may have. You use causal graphs and do algebra to generate the expected pattern of probabilities, i.e. correlations, a database, and then you calculate probability of y if I do x. You look at the correlation patterns in various situations, various subsets of your data to determine if the patterns support or refute the hypothesis model of do x causes y, and you accept or reject the hypothesis model based on a probabilistic estimate, similar to how you do it in the traditional method. And if the model's not supported, you revise and do it again, hopefully with a new set of data. We don't want any overfitting there, okay? So you need a new set of data to test and revise. So wait a second, are these two the same? Where are they different? Where are they similar? And I would argue there's some similarities and some differences. The big similarity, neither one of them proves causation. It's just a method of collecting evidence that causation exists. For testing causal hypothesis in an existing database, the new method clearly seems to have an advantage over the old, because we were just told you can't do it in the old, in the conversation. All the new is designed to do it. Testing causality models when treatment is unethical. I can't make people smart, so maybe I better use the new method, because I can look at databases and gather evidence of causation. Testing a new drug. This one I have to get it to the old model, because I don't have any data sets on a new drug. So I can't use the new approach. I gotta go back to the old approach of randomization and treatment and trials, and blind treatments. Testing a causal relationship in a natural environment. You know, when I brought those freshmen into that little cubicle and sat them down, it wasn't exactly where they normally live. If nothing else, they were mostly sober when I came in. So right away, we've got a big confounding. So this lets you gather data in a natural environment and test it. I have a question mark by the traditional method, because it's hard. It's very hard to do, but I won't say it's never been done or can't be done. There may be ways to sort of randomly selecting groups, fish or something, and then treating one group and not the other, so they're in the natural environment. But it's tougher than the new method. Exploring the nature of confounding variables. Again, I gave a question mark to the traditional method. You can do it, but you got to have additional control groups. You may have to run additional experiments, so it can get complicated and take a lot of effort. So I sort of put a question mark there. But the new method, a lot of it's developed around is confounding. Okay, train my robot to use causal reasoning as it goes through its world. This one clearly the new method has an advantage, unless your robot's going to be running around doing, random trial experiments all day long. Big advantage there. And getting help from existing software, I think I mentioned this, you can do that for both methods. It's out there. Although not quite as much documentation on the new method as we're learning. Okay, so just so we get back to the title, here's an algorithm for your autonomous robot. It generates a causal model from correlational patterns in its data sets. Or it may get it elsewhere. I guess these robots can read now, so he sees someone talking about a causal relationship, and now it's got a hypothesis. It calculates P of Y if it does X to decide if there's a causal relationship, and it does this from its existing databases that it has there that has all these correlations, and it can generate some causal graphs. The software package actually does that for you, puts up, and you tell it how you think these are related, it generates a little causal graph for you. And it uses do algebra. It adjusts the model to better align with the evidential patterns. It then tests the transportability or generalizability of the model with new data, again using correlational analysis, causal graphs, and do algebra. So that's the way I think your really smart robot's going to work. And you repeat the process. Okay, how am I doing on time? We're okay. This will tell you, I'll go real quick here and we'll be done. Does it work? There's always that question. I knew someone would want to know that. One way of seeing if something works is try it on something where you know the answer and see if it gives you the same answer. So what I'm going to summarize real quickly here is a study that was done where they tried to take a randomized trial experiment and that had some outcome, and then tried to see if that would be replicated if they used a new method. It was done by a couple of Harvard political scientists. They actually won a prize for this study, so someone thought it was a good study. What they evaluated was a government training program that taught occupational skills, job search skill, work experience training. They then tracked the earning history of people who had gone through the course and some that didn't take the course to see if there was a difference. They also had a control group because they thought motivation would be important. So even if I say, okay, this group's going to take the course and that isn't, if you're randomly assigned, there may be motivational issues where this group really doesn't want to be there and they're sleeping through the course. So they actually had a group of people who had volunteered just on their own to be part of this program, who was sort of the high motivation control group. So the causal model that they tried to mirror, they said, well, suppose we use these new techniques, and this is the model we're testing, that motivation actually impacts on the likelihood they'll sign up, whether they'll show up, and what their earnings are. And you knew the outcome was going to be good. They essentially found exactly the same thing and couldn't find any kind of systematic bias one way or the other in what they were finding with the new method. So we have at least one study apparently that says, hey, this really works. Okay. Before I show you the resources, a quick thanks to a few people. Joel is a research psychologist who challenged everything I said and told me how stupid I was and quit wasting his time. But it was because of those challenges that led me to try to explain this. And Bud and Angie are in a little study group we had that set out to study stock investments, but I hijacked the group to work on causality. So they've been really helpful in looking at the presentation. My wife, Nancy, who anything that looked like English in the presentation is the result of her input. And Chang helped right from the beginning in terms of encouraging me and helping on the presentation. So, two resources here. One is the book of Why, and that was written as a popular book, you know, for the general population. The one I couldn't get anybody to read. The other one is actually a primer, a statistical test book. And in a lot of ways, I found parts of that more understandable, even though I didn't fully capture some of the math that's going on. I know what they're doing, and it was clear to me, but it may have been because I read the first book first. But that's a good little book, and I actually whined to Wiley and got all the answers to the workbook, convinced them we were going to do something here that would help sell their books, so they should give that to me. Microsoft has now come out with a do-why library, and Bud and Angie and I actually got it up and running in a Colab Jupyter notebook, and so we've been playing a little bit with that. And
You and
looking
Angie
for,
got it up and running.
huh? Well, it was a group input. And so that's at this link. This link's what I thought was really a good talk. I haven't seen it all the way through. Did you watch it all the way through, Bud? Or?
I got about halfway through.
Halfway through, but
It was good.
yeah, he does two things. He tries to explain in a lot more additional examples why causation is so critical, and then B, he tries to explain some best practices in testing your causal models. So I decided I'd put that on there. And the third thing is I'm really sort of interested, if some people are interested, trying to form a study group that would learn with me. If you're thinking I'm going to be the instructor, you may not be the person for this group. But I just think it's fascinating stuff, and I think it's important, and I enjoy continuing my lifelong quest to understand how do you gather evidence to show causation. So you can email me. I'm on Slack. I have commented on the general channel, so I should be easy to find up there. And if you're interested, shoot me, and I'm going to start building a list of names, and of the people who are interested, we'll get together and organize ourselves. Okay, questions? I'm under an hour.
I was just going to, I have, I'm the least capable of the people in this room, but I have been trying to get through the Book of Why. The two most interesting things are that he actually goes back in time and shows how some of these theories are not new. I mean, he goes back 100 or 150 years or even farther with documentation to show that there's been thinking that's been going on, obviously without technology. And then the second is he uses really simple examples like people that eat tea and scones and eat one or the other, and uses that to base his explanations on causality. So it's actually more readable than you might think, given the subject matter. So that's a comment, and then a question. I meant to ask this a few slides earlier. In your example about smoking, introducing tar, we now know the influence of tar, but wasn't that a hypothesis? If you start out with that, you could be wrong. It's in your data set.
You could have been,
There's
but
no
it was in
reason
the, it was
priori to know that's the answer.
it was in the data set, and it correlated with other variables. So it was something you could use to try to generate some additional equations to work with. And that's actually where I got that and learned that bit of history. It wasn't the book of why, it was in the primer, the statistical primer. He takes you through that example in much more detail as to how that's set up. And the part about the history that's interesting is Fisher and Pearson would not let people even say the word causation. It was sort of like, you can't use climate change in Florida, to say the word. And and they would run people out of the society who even started to raise the question, call them idiots, and hound them out. So it set a lot of the investigations back. I'm sure that's why some of my professors told me to go away when I mentioned the word. Any other questions?
Was there a moment, you seem convinced that this is a worthwhile endeavor, and I've read a good part of the book and it seems really good. Was there a certain moment when you decided, hey, there's really something here? Was there a certain example or a moment when you really became convinced that this was a good approach?
That's interesting. I think it was the line that says, and these are the only three kinds of confounding.
Yeah, that is remarkable, yeah.
And I'm like, oh, now the problem seems a little more manageable.
Right.
Although then when you look at the spaghetti chart, it doesn't seem so manageable. And it turns out it's complex. It's got its own set of assumptions. I mean, we use linear regression all the time. But if you only use linear regression when every single assumption was met, we'd never use linear regression.
Sure.
And we don't know as much about this technique when violating assumptions are going to get you in big trouble as we do about linear regression, just because it hadn't been used as long. Although Pearl talks about when things seem really robust, and even if it's not perfectly independent, it's going to work for you when it isn't. But merging science. Fluid.
You showed some cool graphs that you can kind of introspect the graphs and kind of dissect from visually which of the three components kind of make the different the nodes and everything. Is there one optimal graph, or were there many different permutations that are possible? And is it an optimization problem that they're trying to solve?
That's an interesting question, and I'm going to give you the answer to the best of my knowledge. I would go check me somewhere before you tell anybody this. My feeling is, this may be part of some of my own science, that this does rest pretty heavily on developing an a priori hypothesis and then testing that a priori hypothesis. And now that a priori hypothesis can have as many things as you want to put in it, just like when we did experiments using the old method. We could control for variables, have different control groups, run more experiments to see if this made a difference or that made a difference. So, but I don't, as I understand optimization, and I do understand some. I actually goes through the book on once, so but that doesn't make you an expert. But it is not an optimization problem. It's more of an a priori, set the hypothesis, test it and you can adjust it, but then go find another data set to test it on.
And when I read his book and the causal diagrams, one of the things he says is these things should be at least reviewed by an expert in the field to make sure that the arrows are pointing in the right direction and connecting the right dots. So
you have to know all that.
Yeah.
Like you have to identify the count the arrows and where they're pointing to yourself to dump it in the do-why program. I mean, am I asking a question that makes sense? I mean, do you have to
Yeah, no, you're asking a question that makes
so
sense.
like that ugly thing.
I haven't used the software enough to know exactly. I think it generates the graph. So I think you do. I think this is the process. You use the graph to help you set up the hypothesis. You know, I think this is what causes that. But I think there's probably this fork variable that's having an impact on both of them, and you know, there's probably this mediator like tar that's in there. So you go through and draw that. What I don't know, I don't think you input that visually to the computer program. The computer program has some way of you saying, you know, this is this kind of variable and this, that, because the computer program generates the graph. And the example, the one Jupyter Notebook we found and got working.
But does it discover, does do-I discover those things? You have to put it in as part of your hypothesis.
You put it in as part of your hypothesis.
John, I thought that Pearl did talk about traveling back and forth between hypotheses and data. I mean, I do remember part of the book where there was multi-directional. It wasn't just one way.
Well, I think that happens in the traditional method also.
Yeah.
Yeah, when my expected results didn't come out, I quickly. I'm still being graduate school.
Is there some like accuracy of the result that tells you whether it's good or not?
Uh,
Like how do
you-
you throw away the hypothesis based on like a p-value or something? I don't know.
Yes, you do. You get a p-value.
Out of this do-I thing.
Right.
Okay.
You'll get something like, here's the estimate impact, you know, doing X, or doing X will change your this variable by this much, and here's the confidence interval around that.
So it's kind of like regression, but it's all based, but the guts of it are based on Bayesian, I can't say that word, probability stuff.
Right, right, yeah. Yeah.
So
And you can use other things other than linear regression. I'm actually on a chapter right now in this textbook that explains why linear regression is so powerful, and it really helps this method. And you know, it has things like, you know, each way along the line it's going up. Whereas if you've got a curvilinear, you know, some other kind of more complex relationship, it doesn't work quite as well. But you don't have to use linear regression. You can use other kinds of you know, modeling techniques other than regression.
But if you had the same problem, you could throw it into, you could analyze it both ways and then compare those results.
Yeah, yeah.
That became a cool thing to do.
Yeah, right. That's what we do in machine learning, right?
Right, exactly. This is one more thing you throw in there.
Right, and the computer can keep doing this. It's not going to get tired. I may run out of money, but it's not going to get tired. All right. Anything else? Well, you guys have been great. If piqued your interest, send me an email and we'll see who's interested, and we'll figure out what kind of groups we can form that would engage you to the level to which you aspire to be engaged. And hope that the group's smarter than the individual. Good. All right. And if anybody's got any other questions, I'm going to hang around and for a little bit. Not too long. It's past my bedtime.
Are you familiar with the structure equation model?
The what?
Structure equation model. That's, I think it's one of the years ago. It's one that was